Science Max, experiments at large.
Science Max!
Stable structures are what we're building on this episode. Bridges, cups, pencils, blocks, boxes. They're all being built up and falling down. Plus, how stable can you make a structure using fruit as the base? Stay tuned to find out on this episode of Science Max, Experiments at Large. Greetings, Science Maximites. Get your hard hats out because today we're gonna be building things. Like I always say, what's the point of science if you can't use it to build cool stuff? And today's episode is called Stable Structures. Now, stables are the buildings where horses sleep. So, stable structures means... I think I have the wrong kind of stable. Today, we are going to be building a gumdrop dome. And gumdrops are already kind of dome-shaped, but they don't hold a lot of weight. Yeah, can't hold much weight. But you can make it hold a lot of weight if you build a geodesic dome. A geodesic dome means a round shape made out of straight lines, and that's what I've made here. All I used is gumdrops and toothpicks. It's very easy to make, and I'll show you how to do it. First, you need to start with a pentagon, a 5-sided figure. 1, 2, 3, 4, 5. And then stick them all together, obviously, with toothpicks. Then what you want to do is you want to start making triangles. So you stick a toothpick in here and a toothpick in here, and then you put a gumdrop at the top of this triangle, just like this. And then you make another triangle here and here and here, and it becomes a whole bunch of triangles, you see? Easy to make as long as you start with a pentagon on the bottom. Now, once you've built one, I suggest you build 2 more, because then you will have a stable base and you can see just how much weight these hold. Yeah. You wanna max it out? Okay. Let's max it out. Oh, a little collapsing, but still not bad for gumdrops, right? So there you go, the geodesic dome. That's what you research if you want to learn how to build one of these for yourself. But now, let's max this out even more. Okay, now I just need an expert to help me out. Do you like my new interface? It's good, right? Watch this. Oh, wait a minute. That's not, okay. Wait, no, that's not the right gesture for that. It's all gesture-based, so I gotta, this? Nope. This? Nope. That? Ooh, okay. Expert. I want experts. Oh, okay. It's voice activated. Great. Oh, Sarah from Mad Science. She'd be perfect for this. Good. Close. I can leave it running. Sarah?
Hey, Phil. Back here.
Hey, Sarah. Sarah from Mad Science. Great to see you.
Thank you. Great to be here. I like your lab coat. It's a really nice color.
Wait a minute. It's supposed to be yellow. It must have changed to orange in the portal. That's okay because this is not the first time that's happened, so I've installed a little secret thing on the app that allowed me to get a new one from storage.
Oh,
Watch
perfect.
this. Huh. Didn't work. Oh well, I'll get another one later. All right. Anyway, we are going to max out the geodesic dome.
Amazing. That's so cool.
Yeah, so we just want to make it bigger. So how do we do that?
Okay, well, there's a couple ways we could do that. We could add a few more points of connection, change the shape of it, make it a little more complex so it's a little bit bigger. Or we can use the design right now and use different materials to make it bigger.
Ah, okay. Well, you know what? I think we should do both of those things.
Okay.
I think we should make it more complex and bigger, but why don't we start with bigger?
Okay.
But we'll use the simple design right here, and we'll just get like long wooden poles instead of toothpicks.
Perfect, yeah. And then, what will we use for the gumdrop?
I guess we can't get big gumdrops, huh?
No, I don't think so.
What about oranges? Huh?
Yeah, oranges could work.
Maybe, yeah, because you could stick the poles in and then the oranges would be, okay.
Yeah, that's
We'll go to the Science Max Fruit Market and we'll get some oranges.
Perfect.
And I'll get a yellow lab coat. I don't know why that didn't work. Is this a maxed out number of oranges?
I think so.
Or is it just a mediumed out number? We don't really need many more oranges than this.
No.
So, there we go. So we got our oranges. Those are going to be our gumdrops, and
These wooden dowels will be our toothpicks.
we just have to start with a pentagon, right?
Yes.
5 sides. So why don't we just lay that out and see what it looks like here.
We start building this dome the same as the gumdrop dome.
So, like this.
We stick the dowels into the oranges to make our 5-sided pentagon.
Good, like that.
And then we go up from there by making a few triangles and sticking the oranges on the tops.
Oh.
But because the oranges are heavy, the triangles are pretty wobbly. That is, until we get them all connected with cross pieces.
Yeah.
After that, it seems to hold up pretty well.
Okay, let's see if it holds it up. Whoa! That's exciting. That is very exciting. Let's do the same thing. So you make a triangle here, I'll make a triangle there, and then we'll connect them.
Sounds good.
2 layers, orange dome. I'm pretty excited about this. This is nice.
Yeah.
I'm surprised that the oranges actually hold it together because oranges aren't really that strong.
No, exactly. But the structure itself is really strong based on the design of it.
Yeah, because it's all about the shapes, right?
Exactly. And we're using lots of triangles today, which are one of the strongest shapes on Earth.
Ooh, strong. Well, then making something out of a lot of triangles makes it really strong.
Exactly.
Yeah, okay, so let's make that top layer of
All right.
things. We only need 1 more orange.
Yeah.
This will be the one, top layer.
Right in the middle.
1 orange on top with 5 dowels from each point and...
Yeah! Orange juice high five.
In fact, it worked so well, there's only one thing left to do.
Is there a way that we can maybe max it out even more?
Watermelon? Watermelon. We could get the round watermelons. You ever
Yeah.
seen those? They're like the size of a bowling ball or
Yeah.
smaller, a little bit smaller.
That's perfect. And they're nice and full inside, so they should be able to hold the posts into place.
Okay, we'll try it one more time with watermelon. Inside dome high five. Yeah! You may have heard of cup stacking, and if not, you're missing out because not only is it fun, but it's something that kids are the world record holders at. And it's all about, you guessed it, stacking cups. Now, I have learned the pattern, but I'm not super fast at it. The world record is actually 4 seconds, and this is what that looks like. But you can't use camera tricks to help you. You have to practice to get faster. Now, you don't need to use official sports stacking cups, but if you don't know your science, some things will work against you. First of all, these cups have holes in the bottom, which makes them not very good as, cups. Why do they have holes in the bottom? Because of science. You see, when you pull the cups apart, there is air that needs to get inside this cup. If you don't have a hole, like these ones, the air makes them stick together because there's nowhere for the air to get in except for underneath, and they will stick. Once again, let's compare. Also, you want the cups to have some weight because if they have some weight, they'll fall out of each other easily. If they don't have any weight, like, say, these styrofoam cups, it becomes very difficult. And cup stacking with trash cans. Okay, here we go.
Even though these trash cans were heavy, they didn't have holes in the bottom, which means they stuck together. A lot. So why didn't I drill holes in the bottom of these trash cans?
Okay, and then
Well, I needed them in episode 6 to make 11 barrels of slime.
okay. 2. No.
But I eventually did it.
And time. Okay, there you go. The world record in trash can stacking. I know it doesn't seem very fast, but first of all, that was hard. And second of all, I am the only one to do it. So therefore, I hold the record.
Sarah and I have already made a great dome out of oranges. Now we're maxing it out even more, but this time using
Watermelon!
Watermelons! But not the giant watermelons,
Nope.
the perfect spherical watermelons. They'll have to do pretty good to be better than the oranges.
Definitely.
All right, so we just do it the same way?
Same way.
All right.
Let's do it.
I'm sure I'm not telling you something you don't know when I say watermelons aren't great for building structures
This is
with.
super wobbly.
But the fact that we can make a structure using watermelons just proves how amazingly strong a geodesic dome really is.
Have we done it?
Yeah.
We've done it! Yeah, watermelon dome!
All right, we've got our gumdrop dome,
We've got our orange dome!
and we've got our
watermelon dome! These are awesome maxed out domes. What do we want to do to max it out even further?
I think the watermelons were a little too heavy. Maybe we should go back to something lighter.
So we can make it out of gumdrops, which will be like more complex.
Exactly.
And we won't get orange juice raining on our heads all day,
Yep.
which is what happens with this one.
Max Historica. This is Leonardo da Vinci,
Ciao.
one of the greatest inventors to ever live. And this is a pile of wood. One of the greatest piles of wood to ever be piled. Now, Leonardo is going to construct a bridge out of this wood. This is Leonardo's hammer. One of the worst hammers in the history of hammers. Now Leonardo must construct his bridge using no tools at all. No, that hasn't been invented yet. How will Leonardo construct a bridge using no tools at all? Well, he is one of the greatest scientific minds. One of the greatest scientific minds in history. Oh-ho! Each piece of wood is supported by another. And that's what's known as Leonardo da Vinci's self-supporting bridge. Leonardo's done it! But there is a flaw in the bridge. It's very strong when you apply downward force, but not so strong when you push on it sideways. Fortunately, Leonardo can devote his great mind to figuring out how to clean up his workshop. Haha! Join me, one of the greatest narrators in the history of narration, next time on more Max Historica. Let's recap. Sarah and I have maxed out our simple geodesic dome, but now it's time to make it even more maxed out. We need to increase how complex our structure is.
So right over here, we actually have a dome that's just made out of triangles.
Ooh, look it. It's nothing but there's a triangle there, there's a triangle there, triangle there, triangle. So all triangles.
All triangles. And see how much bigger it is even compared to our first one?
Yeah.
And that's just by adding more points. Over here, we have one that uses pentagons and triangles.
Ooh, let me see. Okay, so we got, oh, there's a pentagon there.
Yep.
There's a pentagon there. And then we got triangles here.
Yep.
Can we go bigger than this? Because this is good, but this is not maxed out enough.
Sarah had the idea of lengthening the poles
Shish kebab skewers, I love those. I use those all the time in my science experiments.
and making a bunch of pieces that fit together.
So we just make a whole bunch more of these.
Yep.
And then we'll make some sort of big dome. This is awesome!
So we maxed it out, and it worked great. But gumdrops started to become a little hard to work with.
Every time I do one attachment, another one comes apart. So I had to get inside to hold it up with my head.
I think I've got an idea.
Oh, yeah?
Be right back. Yeah.
Okay, but should I get out or should I? It's okay, I can stay in. I could just keep fixing while it's collapsing a bit, but it's okay. Wait, this is inside. No, this is outside. Wait, hold on. Help, Sarah?
Hey, oh, my.
It kind of collapsed a little bit. Gumdrops, they just don't have the strength.
Exactly. I was thinking we could use something a little more sturdy, maybe like some cardboard.
Oh, yeah, and it doesn't move at all. We can totally make this, we'll max this out. I'll just put this over here. Okay,
All
fair
right.
enough. Okay. If you want to build a block tower, you might think the fastest way to do it is just by building a single stack of blocks. But science may have a few things to say about that, and those things would be no. Let's try it with books.
The books are much wider than the blocks, so that will give me a wider base, right? But it's all about the center of mass. You compare how wide it is to how tall it is.
Right now, it's pretty wide and it's not that tall, so the center of mass might be around here.
But if you go high enough, how high it is compared to how wide it is changes a lot. It's getting higher, but not any wider.
The center of mass is probably right around there somewhere, which means it's gonna be really hard to balance that. Whoa, careful, almost. I can do a little bit more, I bet. Oh, careful, careful. Whoa. It'll only get so tall. So there you go. You can never stack a single stack of anything very high. But just in case you don't believe me, let's max it out. Ah, ha, ha. Oh, careful. Now it's time to see how high, whoa, how high I can make a single stack of boxes. Okay, and whoa, 6 boxes! 6 boxes! 6 boxes! Whoa! Can he go as high as 12? Let us find out if I can go as high. Apparently not. Can he go as high as 11? Can he go as high as 11 boxes? Let's find out. Oh, careful, careful, careful. And, ha-ha, a single stack of boxes! Huh. Okay, well, like I said, you can't stack a single stack of things too high, because it will fall. Ha-ha. Science! 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 This is a pencil. You probably have one of these at home and use it for all kinds of interesting things like writing and drawing, and that may be it. But if you have a lot of pencils, you can build stuff. I'll show you some of my favorite pencil builds. Check this out. It's a pencil cube.
If you want to try building one yourself, you build it like this. Get a piece of foam and then lay out 11 pencils this way, and then another 11 that way, so they make a nice square. Then take sharpened pencils and stick them into the foam in all the gaps. Go all the way around, and then keep adding more layers of pencils, and eventually you will have a cube. Now, if you don't have 366 pencils at home, you can do the same thing with toothpicks.
Now, if you want to research this on your own to find the instructions, just try looking up pencil cube. Okay, that's not the only thing we can build with pencils. Check this out, a pencil asterisk. Phil, can you max it out and add some more pencils? Yeah, so I did. I maxed it out with even more pencils. And then I thought, well, could I max it out again? So I did. This is what it looks like with even more pencils. And in fact, I removed the inside pencils and the whole thing still stays together. And then of course, this is the maximum number of pencils you can do with this configuration, because as you can see, it starts to become a sphere and you kind of run out of pencil length. There you go, maxed out pencil structures. Of course, I've used all of my pencils, but that's okay, I will buy some more. I will just write myself a note to buy more. Actually, there are sharpened pencils on the bottom of my pencil cube, so I'll just write this note with the pencil cube. What could possibly go wrong? Okay, ready? 1, 2, 3. And it's still standing! Oh, that one's not sharpened. Oh, here we go. Where'd my book go? Ooh, look at...
Sarah and I have maxed out a geodesic dome out of gumdrops, oranges, watermelons, and more gumdrops. But now we're making one using glue and cardboard circles.
Are those the same distance?
After a bunch of time assembling and gluing, we have a giant maxed out dome.
Okay. There? Are we done?
I think so.
We're done!
Yeah.
Yeah! Max out dome. How many points do we have?
So many.
Do you think we can lift it?
I think
I think
so,
that's the
yeah.
top. Try it.
See,
Okay, whoa. Whoa! Wait, we can spin it!
It was really light and also really strong. Strong enough to hold upside down.
As a fruit bowl, it'd be pretty good. This is so strong. I'm surprised at how strong this structure is. There you go, Science Max, experiments at large, geodesic dome. And now it's sort of a geodesic disco ball. I like it. Whoa, 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 okay, careful. Careful, careful. All right, putting it down, putting it down.
Today we're looking at polymers.
Polymers. Word has lost all meaning.
Plastics, latex, rubber, and our favorite polymer, slime.
Oh, yeah.
All on this episode of Science Max Experiments at Large.
Oh, greetings, Science Maximites. My name is Phil, and I think I might have overdone it with the science. I mean, what's a better use of science than creating a whole bunch of slime? Well, I did, and you know what? It's really cool. Slime. I love slime. It always makes me feel like a mad scientist, but I need a good mad scientist laugh. Yeah, it needs work. Anyway, today we're talking about polymers. Polymers like slime. But you see, polymers aren't really a substance. They're more how something is constructed. And there's all kinds of different polymers. There's slime, obviously, and rubber polymers like rubber. And there's also hard polymers like plastic. Now, polymers are all kind of constructed the same way. Like this. This is a chain. Yeah, so imagine this is a chain of molecules, and all the molecules are the same, and they just repeat in a long line. Now, when you get a polymer like slime, all the chains are not connected or very loosely connected, which means that they can flow over each other like a slime or sort of like a liquid, and they behave like that. So that is slime. But when you get to a rubber polymer, you start to get little bonds in between the chains of polymers that work like this. You see, they still move around a little bit, but they can spread apart, and they become flexible and bouncy. Yeah, I know, a chain doesn't really bounce, but rubber polymers do. Huh? Now, when it gets to a solid polymer like plastic, there's a lot more links, and it's all kind of interconnected, and it doesn't move at all. It doesn't move. Okay, again, harder to tell with a chain, but plastic is very hard and rigid. So let's dive into the world of polymers and make some slime. Yeah, too mad, not enough scientist. I'll keep working on it. Anyway, to make slime, take your white glue and pour in an amount. It really kind of depends on how much slime you want to make. Now, you want to add about twice as much water as that. Yeah, somewhere around there. Great. Now we want to put in just a little bit of soap. Maybe there, that's good. And you want to put in your food coloring. I like green. Green seems like the right slime color to me. It's the right appropriate mad scientist kind of slime. And then you want to start mixing that up till you get the right kind of consistency. That means make sure the glue and the water are equally mixed up. Good. And now we're ready to make it an actual slime by bonding the polymers together by adding liquid starch. Very good. And you want to mix it up.
When you add the liquid starch, it starts to bond the chains of molecules together, changing it from a liquid to a slime.
It's coming along. And there you go, slime. Now, if you want clear slime and not opaque slime, you want to use clear glue and not white glue. But that's basically the recipe. So there you go, slime. Too supervillain? Yeah, okay, well, anyway, all right. Now all you need is an expert to help me max it out. Of course, my interface is hand gesture based, so I don't know if the slime. Oh, hey, there we go. Great. So you get it. Oh, of course. Sarah from Mad Science. Mad Science, they really know their slime. This is great. Okay, I got it. Close. Hey, there we go. All right. Ugh. I'm not sure if bringing it through the portal is such a good idea, but at least I'll have it on the other side. Ugh. I have a pot. Why do I have a pot? I didn't have a pot when I went through the portal. Is someone somewhere missing a pot, or did it just create this pot out of nothing? Huh. Hey, Sarah!
Hi, how are you doing?
Good. Sarah from Mad Science, you're gonna help me make some slime.
Yes, I actually brought some. Oh, this isn't slime. This is a pot lid.
Hey.
Oh,
Well, at least we have a set. Doesn't answer any questions, though. And I guess we're gonna have to make some more slime.
definitely. What kind of slime do you want to make?
What do you mean, what kind? Is there more than one kind?
Oh yeah, there are tons of different kinds of slime with lots of different ingredients and recipes.
Oh, I only know the one. Can you show me all the others?
Of course, let's go make some right now.
Okay, great.
Awesome.
Come on down to Sal's Science Shop and see me, Sal, while you shop for science. This week only, Sal's one-of-a-kind, once-a-year polymer sale. 50 to 75% off anything made of polymers. Rubber? That's a polymer. Polystyrene. When you're eating your next meal, I recommend some polypropylene. Low-density polyethylene. High-density polyethylene. You want some polytetrafluoroethylene? We got it. We've even got polychlorotrifluoroethylene. Do they even know how good a deal this is? Because you're not gonna find that kind of deal just like every day. But hold the phone. Polymers aren't just plastics. Rayon, nylon, Teflon, you name the lawn, we got it on sale. What do we want? Polymers. When do we want them? Anytime during normal business hours. Wool, silk, even cotton. Polymers, polymers, polymers. Polymers, polymers, polymers. Word has lost all meaning. Glue, paint, umbrella fabric, oh yeah. Carpet, you bet that's on sale. Roberta, I'm running out of sale signs. Buy it and I'll put it in a plastic bag, also made of polymers. Seriously, Roberta, we can't have a sale on everything. Oh, hey, even you, even me, the proteins in our bodies, even our DNA, all polymers. So come on down to Sal's Science Shop and get a great deal on your polymers for a limited time. I mean, it'd have to be a limited time, right, Roberta? Because, I mean, I can't discount everything in the store to 75% off. How am I gonna make any money? I mean, are we still rolling? 100 different kinds of slime.
Yes, it's gonna be so much fun, but we're not gonna make 100 today.
Yeah, I know. We're just gonna do our top favorites.
Yeah, it's gonna be super great.
All right, what are we starting with?
So our first slime we're starting with today is some really cool molding slime. Now this slime, actually, if you leave it out overnight, it'll harden and you can make an imprint of whatever you like. So here, we made an imprint of our little tool there. So we're gonna look at a little bit more liquidy slime, starting with this one over here, which I believe you already know about.
This is cornstarch mud.
Exactly.
You hold this.
Sounds
I'm gonna
good.
hold this and we're gonna try pouring it. Whoa, oh,
Whoa.
so, see, it's like a liquid, but then if you do it fast, it's like a solid. All right, what's next?
Over here, we have some other really awesome types of slime. So right over here, we have some crunchy slime.
Crunchy slime.
Exactly.
Why is it crunchy?
Now it's crunchy because we've actually added a few beads inside of it to make it crunchy. So this is some really cool, awesome slime.
Here, you take half.
And you can feel the beads as you stretch it out. It's so cool.
This one is a little harder to clean.
Exactly.
I'll just do that. All right, so what's next?
So next we have some really cool glow-in-the-dark slime.
Glow-in-the-dark slime.
Yeah, it's so awesome.
Ooh, look at how much it glows. That glows a lot. That's super glowy slime. So to do the different kinds of slime, we need the polymer.
Yes,
And then the thing that sticks the polymers together.
exactly.
So the glue is the polymer,
Glue is the polymer.
and the starch is the thing that bonds it.
Yes,
Aha.
very cool.
And then you put the thing in that makes it the kind of slime.
Yes, right before you add the bonding component, because if we keep adding stuff after it's already made, it unfortunately won't be able to take it. So we add our powder before we add our starch in this situation.
Should we go on to the next thing?
Yeah, let's move on to
More slime! Plastic is great, and plastic is everywhere. But the problem with plastic is it isn't very biodegradable. It doesn't break down in the environment. I'm still on hold. Oh, well, there you go. Back for another couple years, I guess. But here's a way that you can make bioplastic. It's fully biodegradable because it's made of natural materials.
The recipe is easy. 2 parts cornstarch, 3 parts water, a few drops of cooking oil, and some food coloring to make it whatever color you want.
Purple, science purple.
Mix it up, and it turns into a paste.
Now what you'll need are two things. One, an adult, and two, a microwave.
Put it in for 30 seconds.
Clock wipe. There we go.
Then take it out and mix it some more until it cools down. Then you can pull it out and use your hands to sculpt it into a shape or take the shape of something else.
Once you put it all the way around, you can turn it into a little flower pot.
Once you've sculpted it,
You need to wait for it to dry, which will take about a day. Clock wipe.
after waiting a day,
Huh? What? It's been a day? Oh.
you have something made out of bioplastic. Like this little flower pot you can use to grow a small plant.
And then when it grows big enough, you can take this biodegradable flower pot and plant it right outside in the dirt, and this pot will biodegrade and turn back into dirt. Pretty cool, right? Well, let's max it out. Biodegradable frisbee! Check it out! It's a frisbee, but it's biodegradable. So you throw it around in the park, but if you lose it, it turns back into dirt. Ha-ha! What, not enough? Okay, clock wipe! Biodegradable lawn chair! Use it for one season and then return it to the earth afterwards. I think this is one of my best Science Max. Okay, bioplastic lawn chair, not as strong as regular lawn chair. We've learned that lesson now, so that's good to know. I mean, how would I have known if I hadn't tried it?
Sarah and I are looking at different recipes for slime.
All right, what do we got here?
So over here we have some amazing foamy slime, which has so many ingredients in it. Here, watch what happens when we start pulling it out.
Ooh, wow. So it's like,
Super stretchy and super fluffy.
here, that's great. Okay, now you gotta hold yours. You gotta hold this end. Okay, and then take some more. And then we take that. And then, yeah. It gets thinner and thinner and it becomes more and more lines of foamy slime.
Yeah. And the last kind of slime we made today is some classic flubber slime.
Ooh.
So much fun.
Now, why do you think is it flubber slime? Because is it really a slime?
It is a slime, yeah. It's super fun and it's super stretchy.
Oh, okay, I get it. Look at that. And it's sort of like a little bit like gelatin.
It is almost like gelatin.
Here, you can have some. There you go. Whoa. Ah, whoa. All right, so Sarah, now what we need to decide is how we're gonna max it out.
Right.
Like, should we just get a lot of slime?
That sounds like a really good idea, but we are gonna need something to put it in because we can't just have slime all over the floor.
Okay, you're right. So we'll get some sort of container thing.
Yeah.
And we'll see how much slime we can make, and then we'll just play with it and see what happens.
Sounds good.
And yeah, we will experiment because it's science.
Yeah.
Okay, high five. Careful high five so we don't splatter. Okay, good. Okay, let's go. This is right.
This is a rubber glove. Well, actually, it's a latex glove. What's the difference? I will get to that in a second, but I'm sure you can agree it's super stretchy. How stretchy? Let's fill a rubber glove with water and see how big it gets. So, difference between latex and rubber. Well, it all comes from a rubber tree. Well, actually, it's a fake tree. It's just to show you how it works. The sap of the rubber tree is collected just like this. There's a spigot, and then the sap goes out, and it's collected. It's the same way that the sap for maple syrup is collected. And this is natural latex. If it's dried out, it becomes natural rubber. Latex generally means the liquid form, and rubber means the solid form. But wait, then why is this a latex glove? The glove is not liquid. What's the deal? Well, generally, latex means water-based or liquid, like latex paint. But it could also mean synthetic latex. That's latex that's man-made and doesn't come from a rubber tree. So, we call rubber gloves because they used to come from rubber trees, but now they're usually made out of man-made latex. But either way, they're super stretchy. I wonder how big this is gonna get. Science! Sarah and I are maxing out polymer slime. How?
Maxed out tub of slime! Whoa! Okay, so how do you feel? Are we mixed up enough?
First, we mix up a bunch of slime in a garbage bin.
So with the polymer chemistry, the polymer is generally a liquid, right?
Yep.
And the bonding agent makes it stick together. So the more we use, the more of a solid we get.
Exactly, yeah.
So we want to split it and make it sort of halfway between a liquid and a solid, and I think we're exactly at the right stage.
It looks perfect.
Oh, yeah. Okay, so let's dump this garbage can in.
All right.
All right.
Then we dump it in.
Oh, gross.
Turns out we needed more slime.
I don't think that's gonna be enough.
I think we may need some more slime.
Yeah, how much more do you think we need?
So we added 11 more.
Ah, delicious.
Perfect.
Last one. Oh, yeah.
Then we experimented.
Oh, yeah. We have a giant tub of slime.
Because the slime is stretchy, it created amazing bubbles.
So do you think I could blow a bubble with the slime?
Well,
Do I-
maybe not you, but
do I
definitely
wanna
the air
try this?
compressor.
No, no, I'd have to just put it on my face. I think I've
Yeah.
already got it on my face.
Then there was only one thing left to do.
We get in this slime.
Can we do that?
We can totally do that. This is Science Max.
That's so exciting!
Going swimming in slime.
Yes!
Who's going first?
You are!
I am, obviously. All right, this is how Science Max does polymers. 3, 2, 1. Plastic is everywhere, but what can we do with it aside from recycle it? Well, we can reuse it to make cool plastic charms. But you're gonna need the right kind of plastic, and you need polystyrene. Just look for the little number 6 inside the recycle symbol.
Cut out some plastic and decorate it however you want.
There we go. Haha, check it out. The Science Max logo. Also, I've made a couple other things. I've got a chemical symbol, an atom, and this is me in some slime.
Then get an adult to help you put it in the oven or
Toaster oven.
at 350 degrees. It only takes a few seconds for the plastic to shrink to 1/3 its size.
The reason why this happens is when plastic is manufactured, it's heated and stretched out and then cooled, and it sort of freezes in that stretched out shape. And when you reheat it, it shrinks back down to the unstretched shape.
Get your adult to take it out and wait for it to cool, and you'll have yourself some small plastic designs you can use for keychains, bracelets, name tags, bookmarks, whatever you want, all using the power of polymers.
Awesome. I'm gonna make all of those. What was that again? Keychain, ornament, magnet.
Magnetic putty in 60 seconds.
This is magnetic putty.
Thank you.
This is magnetic putty.
Then take.
This is magnetic putty.
26.
This is magnetic putty.
2,635.
This is, this is magnetic putty.
I can't count this high.
This is magnetic putty. Magnetic. Oh, it's not a magnet. It's attracted to magnets. Oh, that makes more sense. This is magnetic putty, and this is a magnet. The putty is made of polymers, which means it can flow over itself. It also has lots of iron filings in it, which is why it's attracted to magnets.
This is what happens over several minutes.
And there you go, magnetic putty.
Okay, so where were we? Oh, yeah.
3, 2, 1, yeah!
And remember, don't try this at home.
Slime!
Sarah and I enjoyed our maxed out tub of slime. So let's recap. Slime is made of polymers. Polymers come in a lot of different forms. It's all about long chains of molecules. And none are more fun to swim in than slime.
Do I have slime here?
Ooh, yeah, definitely.
Slime here! Oh, slime!
Well, there you go. Science Max experiments at large. Polymers. Slime. Yeah. High fives. Yeah. Slimy high five. Yeah.
Today it's all about opposites. Things that float and things that don't. Water and gravity.
Gravity?
What goes up doesn't have to come down. Unless it's built, you know, poorly. All on this episode of Science Max Experiments at Large.
Greetings, Science Maximites. My name is Phil. And I am Opposite Phil. Opposite Phil. That's right. Blue lab coat, yellow shirt, evil mustache. I see. Anyway, we're looking at opposing forces today. That's forces that make things go down and forces that make things go up. Right, things with more density and things with less density. Gravity and the opposite, which is anti-gravity. Anti-gravity isn't really a thing. Well, I have to do the opposite. Right. Buoyancy. And buoyancy's opposite, which is girlancy. No, girlancy is not the opposite of buoyancy. You know, you're not helping. Right, not helping. Opposite. Haha. Hello. Goodbye. Today we're going to be making a gravity-powered boat. Ta-da! It's pretty easy to make. You just put water in the top here. Gravity of the water pushes it out the straw, and the boat goes forward. And it's super easy to make. You only need 4 things.
A piece of styrofoam, a plastic cup, craft stick, and a straw. And the tools you'll need: a pen, a craft knife, and the help of an adult, and science glue.
Which is the same as regular glue, except I only use this glue for science. You take your styrofoam and you cut it into a boat shape. That requires the knife and the help of the adult. Then take your cup and draw the circle that your cup will sit in. And then you want to put 2 slashes with your craft knife in there. Again, get the help of an adult if you need it. And then start carving out the styrofoam with your finger and make a nice little indent just like this for your cup to fit in. See? And then it fits in nice and snug. So then what you want to do is you want to make a hole in the cup. You can use a pencil. The hole has to be just big enough for the straw to fit in. First, you want to take the straw and dig up in this direction so that it will be a nice angle for the water to come out, and then you want to get the straw back up into the cup like that, and then glue it so that it is not going to leak any water. And then in the final step, and this is your choice, you don't have to do this, but you can use your craft stick and you can make a rudder, or if you want, you can make a whole keel, which goes just like that, and it is right in the middle of the boat, and this helps the boat go straight, because sometimes the straw goes off to the side one way or the other. Okay, water-powered boat. Actually, it's a water and gravity-powered boat. You see, what you do is you fill up the cup with water, and the gravity of the water in the cup pushes it out the straw, and the boat goes forward. And this is what it looks like in the water. You fill up the cup, and the gravity pushes the water out that way. The buoyancy of the boat keeps it afloat, and good old Newton's third law: for every action, there's an equal and opposite reaction. The water going out the straw this way pushes the boat that way, and it works pretty well. Whoa, if it's going straight. That's why we have the keel. Okay, so gravity-powered boat. Time to max it out. But first, I need an expert to help me. Oh, of course, Michaela from the Ontario Science Center. Perfect. All right, and let's go. No! I stuck myself! I didn't get wet! Now I'm just gonna get it. No! Oh. how maxing out? This. The water gravity boat. It's pretty awesome. And what you do is you put the water in the boat, and then it does this, and it propels itself along. So, we're gonna max it out and make it super awesome. So what do you want to do that?
Oh, man, well, what if we just think about making everything bigger?
Okay.
Right? Like, first we're gonna need a bigger container.
Okay, well, that's a good idea. Tell you what, I got my waterproof portal ordering device. So I'll order some sort of a bin.
Yeah,
Like a big
yeah.
plastic bin. Okay, hold on.
That'd be awesome.
Hold on. Here it comes. Oh, there it is. Okay, so a big plastic bin.
Yeah, and then, you see this straw here? What if we had something like that, except bigger,
Like a pipe of some sort?
yeah, like a big pipe.
One pipe coming up.
I need to get myself one of those.
Yeah, but it doesn't always work, so. Oh, here it is.
Wow.
So, bin is the cup,
Yeah,
pipe is the straw.
yeah.
So now all we need is the boat.
Yeah, the platform itself. I think we need something that's gonna be really stable because we're gonna have a lot of weight this time.
How about like a surfboard or one of those stand-up paddle boards?
Hey, that's a good idea.
Yeah, okay, check this out. Uh-oh,
Oh no,
water stopping.
that doesn't look good.
I think it might have gotten stuck.
Oh,
We'll have to go get it. Because the water's still running and that might overflow,
man, it's
so.
stuck somewhere.
Buoyancy is the tendency for things to float. Things like this balloon, or this ball in water. But it doesn't float on its own. The helium is less dense than the air molecules around it, and they fall past the balloon and push it up. The ball is less dense than the water around it, so the water molecules flow around the ball and push it up. This happens because water is a fluid. The particles flow around each other. This works because air is a fluid, and I know what you're thinking. You're thinking, Phil, air isn't a fluid, but it is. Usually we think of fluid as meaning a liquid, but in this case, fluid means anything where the particles can flow around each other, and that includes air. But you know what? It's hard to see the particles in water. Same thing with air. I can say it, but it's really hard to see it. Now this is sand, and it behaves like a fluid too. Well, sort of. Check it out. Look, it's made of a whole bunch of very fine particles, and it takes the shape of its container. But watch this. I put a ball in the sand, and it doesn't float. Now, the ball is less dense than the sand, but it doesn't float because the particles of sand have a little bit too much friction right now. But watch as we move them around and reduce the friction by adding some air. Now, the sand is behaving like a fluid, and the ball floats. Let's see what else floats on sand. How about this pumpkin? Yep, that floats. How about this block of wood? Yep, that floats too. How about this styrofoam ball? Yeah, that definitely floats. Look at that. The sand is a fluid right now because all of the little particles of sand are moving around. But watch this. If I turn off the air, everything freezes in place. Nothing floats anymore because the sand is no longer behaving like a fluid. So there you go, buoyancy. It all depends on the density of the thing and the fluid it's surrounded by. Huh? Science.
Michaela and I are maxing out our gravity-powered boat. We had a bunch of maxed out materials. We just needed to get our surfboard.
So we got our giant bin,
We got a giant tube. Water's gonna come out of this end.
and we've got a valve here, which means we can fill the bucket, and then we can turn on the valve and see what happens. So,
Whoa. Hey.
okay, you ready?
Yeah,
Now we're
here
gonna turn on the
we go.
valve, and that means now the water is flowing through.
Ooh,
Hey, it's working.
not bad.
Right on. Whoa, look at that. This thing is really working.
Yeah, it's taking off now.
So, okay, this is good. It's going about walking speed. Now that it's working, how do we max it out?
Our fuel here is the water, so
Yeah.
what if we just had even more water?
And it doesn't last long, does it?
Maxing out our boat even more is easy. A bigger bin for more water, and a wider pipe to move more water for more thrust.
Okay, so a bigger bin
Yeah.
is a lot harder to fill because it's hard to get to the top of it.
Well, you're working against gravity, so it's gonna work for us.
I can really appreciate the amount of water that we're putting into this. That's 4 buckets full.
Wow.
This is 5 buckets.
We open up the valve and it starts to go.
Yeah,
Working.
it is working. Look at all the awesome bubbles. Okay,
That works really well.
it really, yeah, it's definitely
Wow.
faster than the other one. I think it's the larger pipe, and we need more water because it doesn't last very long.
Check it out. It looks like it's going even faster now that we've lost a bit of the water.
Less weight.
Yeah.
This is working great, so now how do we make it even better?
Okay, well, the only force working with us right now is gravity, right? Of
Right.
the water coming out. What if we add in an extra force?
And we could squish the water down to go out faster. Okay, watery high five. Okay, we gotta get it's way over here. Come on, we gotta get it. I want to move the water from this container to this container. Now, I could just pour it, but what if it's too heavy? It's too heavy! Help me, science! Well, science to the rescue with this! A clear plastic tube! Ooh, science-y. Okay, watch this. I'm gonna make a siphon, and it's pretty complicated, so follow along. Are you ready? I stick one end in here, and one end in here! Whoa! Yeah, I know, it's not working yet, but that's because we haven't added the science. First, we need to add a little bit of suction and suck the water through the hose like a straw. It has to go over the highest point. Watch this. And there we go. Look, the water is going up. I can even make the water go up even more, and it still works. But why does the water go up? Water doesn't like to go up, right? Well, the reason why is because there's more water going down than there is going up. So that creates suction on this end, and the gravity of this water pulls that water up. So gravity is doing all the work for us. And that is a siphon. Huh? So now let's max it out. This is the same container of water, but now it's colored slightly blue so you can see it go all the way up through this hose. The only really hard part about this is sucking the water all the way up to there. Okay, here we go. I got it working. Now, the reason why it's working is because there's just a bit more water on this side of the tube than there is on this side of the tube.
With a siphon, it doesn't matter how far you go up, as long as the water on one side is lower than the other.
Science. You know about helium balloons, right? Helium is a harmless gas that is less dense than air, which is why helium floats.
If I was to breathe some helium, my voice sounds higher because helium is less dense than normal air, so my vocal cords vibrate faster. Ah!
But have you ever wondered, is there a gas that's more dense than air? There is.
It's called sulfur hexafluoride, and it's much more dense than air. So if I was to breathe some, my vocal cords would vibrate slower, making my voice lower. Ha 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 ha!
This container is full of sulfur hexafluoride. Ooh, I know, it's invisible, you can't see anything. But watch as I blow some bubbles. The bubbles are floating on top of that layer of sulfur hexafluoride.
The bubbles float because they're full of regular air, which is less dense than the sulfur hexafluoride.
In fact, a balloon will float on this as well. The balloon floats lower because the weight of the latex also drags it down a bit. But the bubbles and the balloons are floating on a sea of sulfur hexafluoride. And it is like a sea because it's a fluid just like water, but it's more dense than regular air.
Science! It's awesome!
Michaela and I are maxing out our gravity-powered boat. It was already working well, but now our idea is to try squishing out the water so it gives the boat more thrust. We just had to come up with a brilliant idea how to do that.
Garbage bag! Garbage bag! Yeah, garbage garbage bag! Okay, maybe we should explain the garbage bag.
It's okay, so the garbage bag is attached to the pipe at the back end. There's a hole in the garbage bag. Well, we fill the garbage bag with water. Then we tie the garbage bag tight. Tie the knot so the air doesn't get out. Now that we've got that, we use bowling balls! And we put the bowling balls on top of the garbage bag, and this will, whoa, squish the water out.
Really is pushing on that bag.
Okay, ready? Okay, let's see.
Hey, it's moving.
Our bowling balls were squishing the water out, but the boat didn't seem to be moving much faster.
I think the bowling balls made the whole thing too heavy.
What if we raise the bin up?
If it's higher up, then there would be more force due to gravity.
Yeah, so we have the bin on like stilts or something,
Oh my God.
and then it has to fall further, and then maybe the water's going faster.
I love that idea.
Okay, good.
Yeah, let's try it.
So what we need to do is get
Wait,
this.
no.
Oh, I thought this is the shallow pool.
Yeah, no, that's
no,
over
that one's
there.
that's that one.
Yeah, not here.
Max Historica. Long, long ago, in the time of ancient Greece, there lived a genius named Archimedes. One day he was in the tub and he noticed something.
Oh, hello. Look at that. When I get into the tub, the water level goes up, and when I get out of the tub, the water level goes down. Ha ha! Eureka!
I, don't get it.
Well, I can calculate how much volume something takes up by how much water it displaces.
Yep, still not with you.
Now, I'll give you an example. How much water would be displaced, pushed aside, if I put this ball in the water?
It's light, so not much.
Ah, it doesn't matter how heavy it is. It only matters how much space it takes up. Watch. Ha! You see? The same volume, huh?
I think I see.
How much water will be displaced when I put this bowling ball in?
More because it's heavier.
Ah, nope. It doesn't matter how heavy it is. It only matters how much space it takes up. Watch.
Oh.
You see? A simple and easy way to measure something's volume.
Archimedes, one of the greatest and cleanest scientists in history. Join us next time for more Max Historica. The metric system in 60 seconds.
The metric system is a way of measuring things. Water boils at 100 degrees Celsius, a kilometer is 1,000 meters, but few people realize just how interconnected the metric system is. First of all, it breaks down to a base 10 system. Everything is 10, 100, or 1,000 of everything else, and it's all based on water. This is exactly 1 liter of water. It weighs exactly 1 kilogram. It fits into a cube 10 centimeters on each side. It boils at 100 degrees Celsius and freezes at 0. And this happy little fellow is 1 milliliter. It fits into a cube 1 centimeter on every side. It weighs exactly 1 gram, and the amount of energy required to raise this 1 degree Celsius is 1 calorie. The metric system, everything interconnected and all based on water. Ha! Oh. Uh-oh.
Michaela and I are experimenting on our maxed out gravity-powered boat. Trying to squish the water out with bowling balls added too much weight for it to make much of a difference. So now we've raised our tote higher up, which means the water will have farther to fall and be going faster when it comes out.
And I got a totally awesome name for our boat.
Tell me, what's up?
Totes McBoats.
That's a totally awesome name!
Totes McBoats? Yes! Okay, so are we ready to fire up Totes McBoats?
That's right, yep.
Okay, I'm gonna turn on the valve. Okay, ready? And let go. Totes McBoats!
What we hadn't considered is that much weight that high up would be tippy.
Totes McBoats no longer afloat.
We needed a way to solve the tipping problem first.
You know what we need to do?
What?
We need to build an outrigger.
All right, so check it out. This time we have an outrigger, which means our boat's gonna be a whole lot more stable. It's not gonna fall that way because this thing is floating. And it's not gonna fall this way because it has a lot of mass as well. I think we're almost ready, eh, Phil?
Yeah. Okay, are you ready?
Ready?
Okay, let's do it. Turn on the valve.
Here we go.
Go, Totes McBoats. Oh, yeah. Yes. Yes. Totes McBoats. Oh, the outrigger's pulling it to the side. Oh. In the
gravity-powered water boat worked great. The water ran down from high up, giving it more speed due to gravity, but no more mass than before. And our outrigger kept the whole thing from tipping over. Totes McBoats was a success.
Thank you very much, Science Max Experiments at Large, gravity-powered boat, otherwise known as Totes McBoats! Totes, come back, Totes! Come back!